If we zoom 26,000 light-years deep into the center of our own galaxy, the Milky Way, there is an object lurking there with a mass between 4 and 4.5 million times the mass of our own Sun. It is a bright and very compact astronomical radio source, a supermassive black hole, which we call Sagittarius A star. A big thank you to Blinkist for sponsoring this video. In 1931, an American physicist and radio engineer who was working for Bell Telephone Laboratories named Karl Jansky first discovered a source of noise emanating from the Milky Way. This was a faint and steady hiss of an unknown origin. The location of maximum intensity rose and fell once a day, leading Jansky to initially believe that he was detecting radiation from the Sun. After a few months of following the signal, the brightest point moved away from the position of the Sun. Jansky also determined that the signal repeated on a cycle of 23 hours and 56 minutes, the period of the Earth's rotation relative to the stars, instead of relative to the Sun. By comparing his observations with optical astronomical maps, Jansky concluded that the radiation was coming from the Milky Way and was strongest in the direction of the center of the galaxy, in the constellation of Sagittarius. In 1974, Sir Martin Rees proposed the idea that supermassive black holes could exist within the center of active galactic nuclei, or quasars. In that same year, scientists Bruce Ballack and Robert L. Brown made the connection between their radio detection of Sagittarius A star and other known active galactic nuclei. In the past 20 years, astronomers have collected enough evidence through the observed motions of gas and stars to suggest that something very massive exists at the center of our galaxy. Astronomers have been unable to observe Sagittarius A star in the optical spectrum because of the dust and gas that lies between it and Earth. It's also only observable during the summer months due to the Sun being in the field of view. Instead, astronomers image Sagittarius A star in the radio spectrum and X-ray spectrum using many different telescopes. In this radio image taken by the National Radio Astronomy Observatory's Very Large Array, you can see the point source in the galactic center, which is surrounded by 3 spiral arms that orbit the massive object at the galactic center. The arms are composed of supernova remnant ejecta gas and dust. These images were captured by NASA's Nuclear Spectroscopic Telescope Array, or NuSTAR. The background image taken in infrared light shows the location of Sagittarius A star. In the main image, the brightest white dot is the hottest material located closest to the black hole, and the surrounding pinkish blob is hot gas, likely belonging to a nearby supernova remnant. This is an X-ray image. The time series on the right shows a flare caught by NuSTAR over an observing period of 2 days. The middle panel shows the peak of the flare when the black hole was consuming and heating matter to temperatures up to 100 million degrees Celsius. The strongest sources of energy arise from these bright spots in the region around the black hole, close to the event horizon, possibly in the accretion disk or a relativistic jet of material ejected from the disk. The Hubble Space Telescope, Spitzer Space Telescope, and the Chandra X-ray Observatory have collaborated to produce this stunning image of the central region of our Milky Way galaxy. In this image, observations using infrared light and X-ray light see through the obscuring dust and reveal the intense activity near the galactic core. Note that the center of the galaxy is located here. The entire image width covers about 1/2 a degree, about the same angular width as the full moon. Each telescope's contribution is presented in a different color. Yellow represents the near-infrared observations of Hubble. They outline the energetic regions where stars are being born, as well as reveal hundreds of thousands of stars. Red represents the infrared observations of Spitzer. The radiation and winds from stars create glowing dust clouds that exhibit complex structures, from compact spherical globules to long stringy filaments. Blue and violet represent the X-ray observations of Chandra. X-rays are emitted by gas heated to millions of degrees by stellar explosions and by outflows from the supermassive black hole in the galaxy's center. The bright blue blob on the left side is emissions from a double star system containing either a neutron star or a black hole. When these views are brought together, this composite image provides one of the most detailed views ever of our galaxy's mysterious core. Since the 1990s, scientists have been observing the orbit of stars around the bright and very compact astronomical radio source at the galactic centre of the Milky Way. There are a number of stars in close orbit around Sagittarius A star, which are collectively known as S-stars. A research team used the European Southern Observatory's Very Large Telescope Array in Chile to study the motion of a star called S2. Here you can see real images of the orbit of S2 around Sagittarius A star. In July 2018, it was reported that S2 orbiting Sagittarius A star had been recorded at 7,650 kilometers per second, or 2.55% the speed of light, leading up to the pericenter or closest approach. It was roughly 120 astronomical units, or just under 18 billion kilometers from Sagittarius A star. At this close distance to the black hole, Einstein's theory of general relativity predicts that S2 would show a discernible gravitational redshift, which was detected, which is in agreement with the general relativity prediction. According to general relativity, supermassive black holes like Sagittarius A star create large curves in spacetime, producing an extremely strong gravitational field. When a star moves close to such a black hole, photons of emitted light are pulled into the field, and the light that escapes and makes it to Earth must climb out of the black hole's gravitational well. The result is that the observed light has lower energy, a lower frequency, and longer wavelength, producing a redder spectrum. In this sense, S2 was an ideal test object for studying very strong gravitational fields and testing Einstein's general theory of relativity. In a paper published in 2018, the discovery of conclusive evidence that Sagittarius A star is a black hole was announced. Using the gravity interferometer and the 4 telescopes of the Very Large Telescope, astronomers were able to create a telescope 130 meters in diameter and used it to detect clumps of gas moving at about 30% of the speed of light near to Sagittarius A star. Emissions from highly energetic electrons very close to the black hole were visible as 3 prominent bright flares. These exactly match theoretical predictions for hotspots orbiting close to a black hole of 4 million solar masses. The flares are thought to originate from magnetic interactions in the very hot gas orbiting very close to Sagittarius A star. As of 2020, the star S4714 is the current record holder of the closest approach to Sagittarius A star at about 12.6 astronomical units, or 1.88 billion kilometers, almost as close as Saturn gets to the Sun. It was traveling at about 8% of the speed of light. Its orbital period is about 12 years. In 2013, NASA astronomers observed an X-ray flare 400 times brighter than usual from Sagittarius A star. The flare observed was at a distance of about 150 million kilometers from the black hole. The researchers have 2 main theories about what caused Sagittarius A star to erupt in this extreme way. The first is that an asteroid came too close to the supermassive black hole and was torn apart by the extreme gravitational effects. The debris from such a tidal disruption became very hot and produced X-rays before disappearing forever across the black hole's event horizon, or point of no return for information. A second theory is that the magnetic field lines within gas flowing towards Sagittarius A star could be tightly packed and become tangled. These field lines may occasionally reconfigure themselves and produce a bright outburst of X-rays. These types of magnetic flares are seen on the Sun, and the Sagittarius A star flares have similar patterns of intensity. An object called G2, initially thought to be a gas cloud, made its closest approach to Sagittarius A star in 2014. At the pericenter, or closest approach of its orbit, G2 was predicted to pass as close as 36 light hours, or 38 billion kilometers from the black hole. Initially, it was expected to be completely destroyed by the encounter and become part of the accretion disk of Sagittarius A star, while releasing huge bursts of X-ray emissions. However, this did not happen. This suggests that G2 may be a dense clump of dust, gas, and other material with a stellar object in the middle, or a pair of binary stars that have been orbiting the black hole in tandem and merged into an extremely large star. In July 2019, astronomers reported finding a star called S5-HVS1, traveling 1,755 kilometers per second. The star is in the Crane constellation in the southern sky and about 29,000 light-years from Earth, and it may have been propelled out of the Milky Way galaxy after interacting with Sagittarius A star. After monitoring stellar orbits around Sagittarius A star for 16 years, Gillessen and colleagues estimated the object's mass at about 4.31 million solar masses. A research team led by Reinhard Genzel have said that their study has delivered what is now considered to be the best empirical evidence that supermassive black holes really do exist. The stellar orbits and behaviour of gas in the galactic centre show that the central mass concentration of 4 million solar masses must be a black hole, beyond any reasonable doubt. In 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for their discovery that Sagittarius A star is a supermassive compact object, for which a black hole is the only currently known explanation. If we could approach Sagittarius A star and somehow survive the extreme environment of gamma and X-ray radiation, we would observe some interesting effects in terms of the behaviour of time. As you move closer to the black hole, the flow of time would slow down due to the gravitational time dilation. If you could observe an object falling into Sagittarius A star, it would appear to slow as it approaches the event horizon, taking an infinite amount of time to reach it. At the same time, all processes on this object would slow down from the point of view of a fixed outside observer, causing any light emitted by the object to appear redder and dimmer, an effect of the gravitational redshift. Eventually, the falling object would fade away until it can no longer be seen. The object itself would be ripped apart by gravity before crossing the event horizon. This process would happen very rapidly, with an object disappearing from view within less than a second. If me or you move closer to the black hole, to the very edge of the event horizon, say 1 meter away, for every hour we spend there, 11 years would pass on Earth. This effect would increase exponentially to where at the event horizon itself, time would stop. Across the event horizon would be an infinitely dense and zero-volume singularity, with the mass of 4.3 million suns. The curvature of space-time would become infinite, space and time would switch roles, and the laws of physics as we know them would cease to operate. A big thank you to Blinkist for sponsoring this video. If you're like me and you don't have a lot of time and you like to get a lot of useful information in a nice, quick and easy format, then this is where Blinkist comes in handy. Blinkist is an app that condenses non-fiction books into text or audio-style podcast insights, which can be ingested in roughly 15 minutes. They have over 4,000 book titles to choose from and listen to, and more are being added every day. They are even available offline. I recently came across a book called Mindfulness, and I really liked the condensed and informative format of the book on Blinkist, which has really improved my meditation and mindfulness practices. Whether you want to wind down, get motivated, or learn something new, you can listen across all your devices with the Blinkist app. So why not give it a go? Click the link in the description to get a 7-day free trial and 20% off your subscription. You will not only get a super convenient way for some quick and compact learning, but you will also be supporting my channel and allowing me to create more videos like this one. Another way to support my channel is through Patreon. The link is in the description. Well guys, I hope you enjoyed this video. Don't forget to give it a thumbs up and share. You can also subscribe for more videos like this one in the future. All the best and see you next time.